Welcome to the stream. It's me, your friend Zero Cool. Today, we're going to take a look at how to create a new challenge on codefights.com. I know this is something most of you guys have the potential to do, whether or not you realize it. So I want to try to unleash that potential today. So what we're going to do is create a brand new challenge from nothing, from scratch. And we're basically going to go through all the steps right here in the browser. So I know I've heard people say things before like, I don't know if I could create a whole challenge. I don't know if I could make all the tests, and I don't know if I could do a good description. I don't have an IDE that I could use to make the tests. I mean, these are all things that I want to try to work through today, and basically, yeah, like I said, go from 0 to 100 on a new challenge. So, I guess we might as well get started with that. So let's take a look at step one. So no surprises, I guess. We've got to start by creating the challenge. So the first thing we want to do, make sure you're in the challenges section. That's where I am right now. And we want to go to this thing right here that says create. So let's click on that. We'll see what happens. First thing you'll notice is you're going to be brought to this screen, the task library screen. We sort of have if you've created a task before, you'll find it right here. In order to create a challenge, you need to create a task. I'd say that's the part that's probably the most confusing out of the whole process. So we'll try to work through that. But anyway, the first thing is if we want to make a new challenge, we've got to make a new task first. So let's go ahead and do that. We'll go to create new, and it's going to make a new task for us. Now, we're going to turn this task into a challenge. That's definitely our ultimate goal here. But before we can do that, we need to reach a few benchmarks, I guess. So the first thing we need to do is give it a title. We won't be able to submit it if we don't have a title. And we need to create at least 3 tests. That's just the minimum number it requires. In terms of which ones are going to be hidden, which are going to be visible, we'll talk about that pretty soon. But the main thing is that we need to start by making 3 tests. Before we can do any of this stuff, I guess, we should probably have an idea. So my idea for what I want to do with this challenge in particular, it has to do with change, coins. In particular, let's say we have a certain amount that we're trying to get, a dollar amount or something like that. And we're trying to come up with the coins to make that amount. The question is going to be something like how many different ways can we do that given the coins that we have, or something like that. That's going to be the sort of idea here. So in particular, actually, I want to make it the sort of thing where it's we want to find how many ways, how many combinations of coins that we can use that involve pennies. Okay, so when I say pennies, I mean a 1 cent coin. We're going to go through the whole details of this thing pretty soon. It's going to be based on the Canadian monetary system. So we've got a few different kinds of coins: nickels, dimes, quarters, loonies, and toonies. We used to also have pennies. And so the idea here is we want to know how many different combinations of coins there are that involve pennies for the particular amount that we're trying to get here. So because of that, I'm going to call the challenge Making Sense. A bit of wordplay on that one. Bonus points if you can get that in your title, but anyway, not required. I'm going to name the first argument here, and in fact, this is going to be the only argument. It's going to be called change, because we're trying to, the premise will be that we've paid for something and the cash attendant is giving us some kind of change, and we want to know how many different ways could they do that? How many different combinations of coins would there be? So it's going to be called change. Now, in this case, we're not really going to add any other arguments, but if we did want to, then we could just go to add input, and now it gives us another option for one of these. I am going to make this one an integer. That's probably the simplest thing we could do, but we have lots of other options for data types we could use. I mean, arrays, matrices. We've even got things like linked lists and trees, although I haven't really seen a lot of user-submitted challenges that involve those kinds of things. I'm going to get rid of this input because we're not going to use it. It's just going to be this one, the change input. The output for this will also be an integer, I guess, because it's the number of ways that we can do this. So this will be an interesting challenge because we're starting with an integer, we're finishing with an integer. There's probably going to be some other stuff that's going to happen like in between there. But the main thing is that it's an integer input and it's an integer output. Okay. I guess we should probably give like at least somewhat of a description to sort of give an idea of what it is this challenge is asking us for. So we'll say something like, given an integer change, find the number of ways or the number of combinations of coins that could be used to form this amount or something like that. In fact, number of combinations of coins, let's phrase it this way. Find the possible number, find the number of possible combinations of coins that include at least 1 penny. And then I guess we could say like the coin values we can use are 1, 5, 10, 25, 100, and 200. There we go. So that's just a very, very basic description. I'm not really writing anything for any of this stuff. We'd probably want to say something about the constraints on this, but for now, I just want to look at this sort of one step at a time. So right now, we're just focused on creating the actual challenge. That's kind of our priority. Let's add a few tests. Like I said, we need at least 3 of these tests. So let's think about it. Let's start with 10 cents. How many different ways could we form 10 cents in such a way that we involve at least 1 penny? Well, let's think of all the ways we could do this, I guess. For 10 cents, we could have 10 pennies. So that's at least one way. We could have 5 pennies and a nickel. We could have 2 nickels, or we could just have a dime. But only 2 of those involve pennies. So I guess the answer here would be 2. As opposed to something like if we had 11 cents, then, well, how many ways could we do this? We could have 11 pennies. So that's one way. We could have 1 penny and a dime, 1 penny and 2 nickels, 6 pennies and 1 nickel, and I think that's it. So 4 combinations in that case. Notice we're talking about combinations here, not permutations, so it's important that order doesn't matter. So we would say that like 6 pennies and a nickel is the same as a nickel and 6 pennies, right? Okay, so 4 combinations there. I guess we'll just say if there's 1 cent, let's say there's 1 way to do that. That's 3, so I guess we don't need to really go any further than that right now. So I'm gonna hit save, and there we go. The task has been created. So this is a really, really, really important part of the process, okay? Because I believe some users are maybe under the impression that at this point the challenge has been submitted, and that is not the case. All right, we have not submitted the challenge at this point. We need to hit done, and now we need to create a challenge by hitting this button from this task. Okay, we could have selected some of our, like one of our other tasks that we had done previously, but this is really the one that I want to do right now. So we're going to select this one. We'll choose a scoring type. I'll just go with shortest solution. You can choose whichever. It's pretty likely that it's going to be posted as a shortest solution challenge, but anyway, you're free to choose whichever one you want. At this point, now that I've got this selected and I've got a scoring type selected, I can go ahead and hit create challenge. And now it's saying your challenge has been received. It'll be published as soon as approved by admins. And we can see our description from earlier. We can see our tests that we put in over here. And we can see that we are the author of this challenge. So that's pretty cool. If we want to make edits and stuff like that, we can just hit this icon right here, the little pencil thing. And now we're kind of at a view that looks like what we had before from the task view. So we can edit it, we can, get the preview of it, etc. So that's kind of nice. If ever we sort of like forget this page, you might look at this and be like, oh no, I lost the challenge, it's gone now. If we go back to create, now like our making sense thing, it's like, no, can't click that. So we might think like, well, what am I gonna do? I still need to make edits to my challenge, but I can't find it. Well, I gotcha. You gotta go over here and go down to created, and now we see our challenge over here, unfinished as it may be. So I guess at this point, we might as well take a look at what the next step is going to be in creating our challenge. Okay, so there are a lot of things we need to do here. We need to make more tests. We need to finish up our description, stuff like that. But the main thing is, before we can do either of those, we should probably have a solution here. A solution that's going to work, that's going to tell us like, yeah, it passes the test, your tests are correct, like, et cetera, right? Sort of an intended solution. And that's generally a good thing. If you're going to write a challenge, you probably want to know how to solve that challenge. Okay, so I do have a particular type of solution in mind for this one. I'm thinking, because we're trying to find the combinations that involve cents, what we could do is something like this. So we could say, find all the combinations of coins. Find all the combinations of coins, and then find combinations that don't have any pennies, and then just subtract the two. That's going to be kind of the idea here. Okay, so we're going to find, in order to find the combinations, like just the combinations that involve pennies, we're going to find all the combinations and then find the ones that don't have any pennies, and by subtracting the two, we'll be left with just the ones that have pennies. Make sense? Hopefully. Anyway, we'll go over this in a fair bit of detail. Now, in particular, the solution that I have in mind for this one is a dynamic programming solution. So let's go over that. We'll talk about dynamic programming, kind of how it works, sort of thing. And then from there, we'll work up to having a full solution here. I guess we want to do these one step at a time, right? So finding all the combinations of coins, and then finding just the combinations that don't have any pennies. So the first thing I want to do is make an array. It's going to be called values, and it's going to represent the coins that we have. So 1, 5, 10, 25, 100, 200. Okay, so pennies, nickels, dimes, quarters, loonies, and toonies. So now that we have that, we could say something like, I'm going to make a new array here, and we'll call this one something like coins total. Okay. So coins total is going to start out as an empty array. It's going to be sort of like our dynamic programming array. So we're going to build this up kind of one step at a time. And ultimately, I guess for now, let's just return coins total to see kind of what it's looking like at this point. All right, so how do we want to build this up? Well, first, I guess if we think about the number of ways that we can get a total of 0, there would be one way that we could do it, and it would be with no coins. That probably seems a little bit absurd, but it's going to be kind of necessary, or at least I think it's necessary for what we're about to do. So typically the way dynamic programming works is it's a bit like, well, okay, if you've got sort of like a recursion problem that has overlapping subproblems. So anytime we find that like maybe we're recalculating some calculations, dynamic programming is probably a good way to handle that. So typically the way it would work is, instead of just finding the answer for this value, like the current input, we'll find the answer for all the inputs up to and including that value, so that we don't have to repeat any calculations on the way there. That's kind of the idea. So how are we going to do that? Well, we'll say for let AMT, which stands for amount, we'll start it at 1 because we've already handled the case where it's 0, which is right up here. So coins total starts with a 1 in there, representing the number of ways we can form an amount of 0. Okay. We want to calculate the next value, so let next be assigned the value of 0. And ultimately, we're going to say coins total. We're going to push this next value onto the end of it. That's going to be sort of the idea here. Okay. In between these two, what do we want to do? Something like this. For const value of values, we'll say if the amount is greater than or equal to this value. So in other words, if we can use this coin, right? So like if the amount is, let's say 7, then we'd say, yeah, we can use a penny. Yeah, we could use a nickel. Ooh, no, we couldn't use a dime. So we would stop it there, okay? So actually, before we go any further, I'm just gonna say else break, because I want this to be sort of efficient in the sense that as soon as it finds a coin that's like too big, it's not going to bother checking the even bigger coins. Wouldn't make sense, right? So we're breaking just this loop over here. We'll continue with like the amount loop, the outer one, but we'll break this one. Sometimes in these situations, I would put like a continue outer, put a loop label on it. But since we want this part to fire, we'll just say break this loop. We'll continue down here. Okay, so what do we want to do in the case that the amount is greater than or equal to the value? And I mean, you might notice that should pretty much always be the case for the first iteration here. Basically, what we want to do is next plus equals our coins total for an amount of amount minus value. So what's this all about? Well, basically what we're saying is something like this. Again, let's say the amount is 7, right? Let's say we make it up to 7. Now, if we've made it up to 7, that means we've gone through 0, 1, 2, 3, 4, 5, and 6 already. So we know those numbers. We can use those numbers. So basically, if it's 7, we say, all right, well, is 7 greater than or equal to 1? Oh, yeah, it is. Okay. Well, then we'll add on to that the amount that we have at 7 minus 1, which would be 6. And we've already calculated that, so we can just add it on. What that represents is basically the number of coin combinations that we can use for an amount of 6. So basically what we're saying is put down that penny, and then we can use 1 penny, and then the rest of like the 6 that we need to spend. How many ways could we do that? We already know. Or we'll move on to the next one. On the next iteration of the values loop, we'll say, okay, so this value is 5. So we could put down the nickel once again, right? And then how many more, what's the remaining amount? Well, it'd be 2, right? 7 minus 5, that's going to be 2. How many different ways can we do 2 coins? So basically what next ends up being is the sum of the number of ways we can, not the number of ways we can do 2 coins, the number of coin combinations for an amount of 2, plus the number of coin combinations for an amount of 6. That's what we would get if the amount was 7. That's kind of the idea here anyway. So at this point, I just want to quickly run the test, and I want to see where this is at. Now, we're having a bit of an issue with this one because we're saying change at 10. It looks like the answer would be 9 here, which is not good. That's kind of way off. So why is that? Like, why is it behaving this way? Well, basically the idea is that we're actually kind of dealing with permutations here as opposed to combinations, right? Because like I said, when we were looking at this and we were saying, all right, it could be, again, for an amount of 7. Maybe I should draw this out somehow. We could probably try to visualize this, right? So if our amount is 7, basically we're getting the coin total at, it's an array, so I'll make that square. The coin total at 6 plus the coin total at 2. And the 6, this is like, if we're spending 1 penny or we're adding on an additional penny to each of those combinations, this is if we're adding on an additional nickel to each of these combinations over here. So how many coin combinations are there for 2 cents? Well, there's really just 1, and that makes sense, right? Because it would just be 2 pennies. So the combination that we're actually getting out of this is 2 pennies and a nickel. When we look at this one over here, we're saying, all right, so how many ways can we form an amount of 6? How many coin combinations are there for an amount of 6? And in this case, well, there should really only be 2 coin combinations for 6. It should be that we could have 6 pennies, or we could have 1 penny and a nickel. But here's the problem. 1 penny and a nickel plus an additional penny would be 2 pennies and a nickel. And we've already considered that case over here. So we're looking more at permutations here than we are at combinations. We want to make sure that we're considering a case where order doesn't matter. So it's actually not going to be enough for us to use one-dimensional dynamic programming for this. We're going to have to use 2 dimensions. So I guess we'll scrap all this. Or at least most of it. I think we can still use the values, and we can probably still use the coins total thing that we had earlier. Yeah, well, for now, let's see, what do we want to do? I guess we'll start it at 1. Is that how we want to do this? Maybe not, because we are going to make this 2-dimensional. Okay, so the idea is that instead of just having one array containing all of the amounts, we're going to have an array of arrays containing the total amounts, where each row represents a different coin limit, essentially. So basically what we're going to start with is the number of ways that we can the number of combinations of coins that can give us the given amount at, index j or whatever, column j, given that our limit on the values is going to be, up to and including a certain coin, right? So we'll start, row 0 will be, I guess, no coins. Row 1 will be if we can use pennies, row 2 if we can use nickels, row 3 if we can use dimes, etc., right? And that's like up to and including, so like dimes and nickels and pennies, etc. Okay, so we're starting out with coins total, but really I think coins total should be something more like a matrix, right? An array of arrays. So the first array I want to put in it, it's just going to be an array of length change plus 1. Plus 1 because we need to go up to and including the specified amount of change, and we also need 1 at index 0. Now I'm going to fill this with, I guess, 1s. Yeah, because actually, wait. Maybe I should fill it with 0s. Would that make more sense? Because we're looking at the number of ways we can do this with basically 0 coins, right? Actually, hold on. I have an idea. Let's flip this around. We'll make the first row, or like the 0th row, we'll make that the sort of like pennies row. So if we're dealing with pennies, right, if we're talking about the combination, like all combinations of coins, we'll say, well, basically for any amount, there's just one way to find a combination that only involves pennies. It's just that number of pennies, right? If you have an amount of 7 pennies. You got an amount of 11, it's 11 pennies. You got an amount of 237, that's 237 pennies. Okay, so that's basically our coins total if we're including all coins. This is nice because it means we'll easily be able to switch this to a 0 for when we want to find the combinations that don't have any pennies. We would just say, no way to do that, no way to do that, no way to do that, sort of thing. Okay, so that'll be cool. But for now, we'll just deal with it like that. What do we want to do from here? Well, I guess we want to do a loop. For this loop, I think we'll just say something like for const value of values. Because like I said, we want to look at like one coin at a time sort of thing, right? We want to make sure that we're not like just looking at every single coin value right off the bat. Each row is going to have like a certain coin value. That's going to be the idea. Okay. So I guess we could do something like this. We'll just say const next row, and it's going to start out kind of like what we had before. So an array with just a 1 in it. The idea is that if we have an amount of 0, no matter what set of coins we're dealing with, there's only going to be one combination of coins that's going to be usable, and it's going to be no coins. That's kind of the idea. And that might seem a little weird, but it's what sort of kicks off our dynamic programming array. What we'd find is if we didn't include this, we would have much fewer numbers in here. We wouldn't have that like kind of base case to get it started. Okay, so within this now we'll do the amount thing. So we'll say let amount be assigned the value of 1, amount is less than or equal to change, amount plus plus. Okay. And then what do we want to do from here? I guess we want to say like next row at amount is going to be assigned the value of what? I guess, okay, well, let's think about it. There are sort of two things that we want to keep in mind. So right off the bat, we're saying that this is like up to and including the current coin value, right? So let's say we were looking at dimes. We wanted to find the number of ways to form, the number of coin combinations that can form this particular amount, whatever amount we happen to be on, that uses either pennies, nickels, or dimes. So right off the bat, we're going to start with coins total at that amount. In fact, I might need to switch this around if we're going to use a matrix. So we'll do something like this. I is less than values dot length, I plus plus. Yeah, and then we'll have to say something like const value is assigned the value of values at I. Oof. A lot of uses of the word value there. Anyway, so we want to look at coins total at I guess, right? Because that's gonna exist already, right? That's like the previous row, basically. Coins total at I, at amount. And then we want to potentially add something to that. So if it's the case that we can use a dime and then still have some left over, like for example, if the amount was 12, and we could say, yeah, spend that dime, and then whatever's remaining, like the 2 that would be remaining, it's just going to be the number of ways we can form that. Okay, so it's the number of ways we can, number of combinations of coins that don't involve a dime, plus the number of combinations that would involve a dime. But we need to be sure of one thing before we do that. We need to be sure that amount is greater than or equal to value, just like we saw before. If it's not, then we're just going to add on 0 to this. If it is greater than or equal to 0, well, that actually means that we would have already gone past this amount, right? Or sorry, we would have already gone past the amount minus the value. So what we can say is basically next row, like the row that we're working on right now, at amount minus value. That's kind of the idea here, okay? So it's the number of ways, number of combinations that don't involve this coin, you know, in this case the dime, let's say, plus the number of ways that do involve this coin. So hopefully that makes sense. And then since we've got this new row here, we'll just say coins total dot push next row. Okay, cool. And now we'll just return coins total at the end. We'll see what we came up with, and there we go. Okay, so that's a lot nicer. We have a 4 here, which I guess is not totally what we're looking for, right? What we'd expect is more like a 2. If we look down here, the 4 here does match up with the 4, so maybe that's better. If we look at this one, the 1 over here matches up with the 1 over there. Okay, so that's kind of good. But let's consider another custom test over here. Let's say if we had 26. Yeah, and I'm not really sure how many combinations there would be for 26 coins, but let's just put in a 0 for now. We don't need to give it an amount. Well, we do need to give it an amount, but it doesn't need to be the right answer. We'll see what the right answer is going to be. So it looks like it should probably be 13, according to what we see here. Something interesting to note is you might be looking at these and thinking, well, those rows pretty much all look the same. Is there like any difference between those? And as it turns out, yeah, there is, but what it depends on is the size of the input here. If we're looking for a value of 10, then it's not going to make a difference when we introduce the quarter, the loonie, the toonie, you know, like that's not going to matter. There's no way we can use those coins. So basically it's going to stop once we get to the 10. So in other words, at index 2, that's the last change we're going to see in terms of the rows there. So maybe we could actually, you know, think of a clever way to deal with that. Like we could say, okay, well, if the current value is greater than the amount that we're like the change that we're looking for, then just stop. Just don't bother looking at the next one. That's probably a good idea. That would be kind of like a micro optimization. I'm not sure if that would make the difference, like in terms of time complexity or anything like that. But it could definitely save us some runtime. Anyway, taking a look at these, so yeah, if we look at the rows here, you'll notice the last change does happen on the one with index 2. Everything beyond that is exactly the same because, yeah, it wouldn't make a difference if you add in a quarter, a loonie, or a toonie. As opposed to if we look at this one, since this amount is greater than a quarter, we would expect a change to happen at index 3, and it does. It's not a big change. It's basically just these guys turning from a 12 to a 13. And I guess that makes sense because all of these amounts to the left of that were amounts that were strictly less than 25. So it's not until the 25 that we see that change happening. Okay. You might be looking at these and thinking, these all kind of look like the same matrix. And that's a good point. They sort of should if you think about it, right? Because like it is the same matrix we're dealing with. We are talking about like the same monetary denominations, like all the same coin values over here. So it shouldn't really make a difference like how this actually gets structured. But what will make a difference is when we actually start to answer the problem, right? Because technically this is not exactly what we're looking for. One thing that I'm kind of noticing about this is basically we've got this matrix, but it's really only the last row that matters. It's only the last row that makes a difference here, and that we're going to use to sort of answer the question. So since we only need the last row, and actually technically we kind of use the previous row as well, like when we do this step right here, we're kind of looking at the previous row. So what we could do is basically just keep coins total not as a matrix, but just as an array. And that way we can just say, okay, coins total like this, coins total at amount. Next row, we can still use that, not a problem. But then instead of saying dot push next row, we'll say it's assigned a value of next row. Because that way we're not going to have to deal with like having all these rows at a time. It's a lot less space in memory. So there we go. And we're basically getting the same stuff. Like the 4 here matches the 4 here. The 1 here matches the 1 here. If we look at this, the 13 here matches the 13 that should probably be here. But anyway, we won't worry too much about that for now. Okay, so that's our total, right? Like that's how we get the total combinations of coins. But what about the combinations that don't have any pennies? So basically, again, the way we're thinking about this is our 0th row represents the pennies, essentially, right? The number of combinations that involve pennies. So now I want to switch this up, and we'll say coins partial is going to be array also with a length of change plus 1, but what we're filling it with now is not going to be a 1, it's going to be a 0, or multiple zeros. It's like all zeros instead of all ones. So coins total is going to be all of the combinations of coins. In fact, here, let's move over our comments to sort of reflect that. Find all the combinations of coins, and then find the combinations that don't have any pennies, and then at the end, we're going to subtract the 2. That's going to be the idea. So it'll be like coins total at change minus coins partial at change. We'll look at that eventually, but for now we just want to see what we're going to come up with for coins partial. Now right now it's just going to be a whole bunch of zeros, which is not all that interesting. So let's actually do some stuff with coins partial. Now I called this one next row, but I'm going to call it next total just to sort of be a little more specific, because we're going to want to do the same thing now, so, or at least something very close to the same thing. We'll say next partial is going to be this thing. Yeah. And then for each of these, as we go through the loop over here, we'll say next partial at amount is going to be coins partial at amount. So basically the number not involving this coin plus the number of combinations that do involve this coin. So again, we'll say is amount greater than value. And if so, then we'll say, okay, well, that means we already calculated amount minus value. Let's go ahead and grab that from the current row. Or 0. There we go. Okay, so coins partial. What are we going to see here? A whole bunch of zeros. Okay, so not exactly what I was expecting for this one, but I guess it makes sense because we didn't include a line like this. So let's do that. So coins partial is going to be next partial. All right. So now it's actually a little bit different. It's kind of interesting to look at this one. So it kind of goes up like every 5, which I guess makes sense. Like all of these are multiples of 5. So yeah, that's not too surprising, I guess. Okay, so we've got a 1 here, we've got a 1 here. So there's one way to get an amount of 0. Okay, there's one way to get an amount of 5. It's with a nickel. There are 2 ways to get an amount of 10. It could be a dime or 2 nickels. There are 2 ways to get an amount of 15. It could be 3 nickels or a dime and a nickel. 3 ways to get an amount of 20. What would the 3 ways be? I guess 2 dimes, 1 dime, 2 nickels, or 4 nickels. 4 ways we can get an amount of 25. So I guess that would be using a quarter, using 2 dimes and a nickel, using a dime and 3 nickels, or using 5 nickels. So notice everything other than those has a big old 0 here, and it's because we wouldn't be able to get that exact amount without using a penny, right? It's only multiples of 5 that we can actually get by using these non-penny coins. So that's kind of the idea there. Looks like our coins partial is working. So now the only thing left is to subtract the 2, right? So let's get this in here. We've got coins total at change minus coins partial at change. And we'll see what we get from that. Okay, so all these seem to be correct. This one, yeah, it's 13. We might as well just switch that one over to 13. I guess we could consider all the combinations that would work there. Maybe we'll list those out in just a minute, but here, just so we can see all green, let's run the tests, and that'll be a nice little ego boost. Oh, feels good. Okay, cool. So one little thing I just want to change over here. I just want to say const big enough is just going to be this thing right here, because we are checking it twice, and that doesn't really make a whole lot of sense. So we'll say big enough instead, and just sort of keep that Boolean, because it's the same thing in both cases, right? So does that still work, first of all? Yeah, okay, that still works. Another thing, I guess, is that we're not really using the I anymore over here. We were using it before because we need to find like the ith row, but now we can just say for const value of values, and we can get rid of this line over here, which is good because it no longer knew what I was. So, okay, cool. Nice. Okay, nice stuff. So looks like this is working. We've got a working algorithm, and that's really cool because we can use that to sort of help us come up with some tests here. We'll use the test to sort of do a nicer write-up with like an example, that sort of thing. We'll also use this to come up with some ideas for what our guarantee constraints should be. But before we do that, I mean, you might have noticed if you look at like some of the interview practice tests and stuff like that, interview practice tasks, what you probably notice about those is that a lot of the time they'll tell you what kind of complexity they want, right? They'll say, try to do this in big O of n. Try to do this with big O of 1 memory or extra space or whatever, right? So they give us the requirements in those cases. They don't really check for the requirements, but it's like, you know, it's a personal challenge. You should be able to rise to the challenge sort of thing is at least the reasoning, right? So in this case, we're not really going to be able to enforce it, just like with these other ones. We can't really say like, oh, hey, make sure it's big O of n, or whatever it is we're looking for, right? So instead of that, what we're going to do is we're going to try to create tests in such a way that sort of forces the user to use like a smarter algorithm that wouldn't work if it wasn't the right complexity. Okay, so we want to try to come up with some tests here. Now, something I just realized though, if we're trying to tell like what kind of tests are going to work here, what kind of tests are going to allow us to sort of force the user to use something smarter like dynamic programming, I think in order to do that, we're probably going to have to come up with a bad solution, like an example of something that's not quite the complexity that we're looking for. So we're going to reset this, and we're going to try to do this just recursively, okay? Because we should ultimately get the same answer, except it should time out for values that are maybe not so big. Okay, so we're going to try the same sort of thing. Yeah, exactly, a most naive interpretation. So here's what we'll do, or at least a somewhat naive interpretation. We'll see. Okay, there we go. So we've got our values. We'll use that. And now, instead of having like the coins total and coins partial arrays, instead we're going to come up with two functions, and they're both going to be recursive functions. So it's going to be change total. That'll be one of them. We'll have an amount, and we'll have coin index as well. Coin index is going to start at 5. So I'm just going to put that in as an optional argument over here. And ultimately what we're going to do is we want to return change total at change, like at the current amount sort of thing. And eventually we'll have, I'll just comment this out for now, but we'll have like a minus change partial at that same change value. So there we go. Okay, we're eventually going to have that, but first I just want to get the change total, make sure that part's working. Okay, so we're doing this recursively, right? So we're probably going to end up doing something like return. Again, we want the amount for basically the amount of combinations, the number of combinations that didn't use the current coin, plus the number of combinations that do use the current coin. Okay, so we're starting with coin index of 5. Basically what that means is we're starting with the toonie over here. By the way, if you're not familiar with that term, it's kind of a weird one, but that's what we call a $2 coin in Canada. The $1 coin has a picture of a loon on it, so it's called a loonie. And the $2 coin was introduced in 1996, and since it has a value of $2, it doesn't have a loon on it, but we just called it the toonie. It has polar bears on it. Anyway, here's what we're gonna do. Value, I guess, is something we'll need to get a variable for. If you hold on just one sec, we'll explain everything that's going on over here. So, great. Okay, nice stuff. So, again, what we want to return here is the number of combinations that wouldn't involve this coin. So we use the same amount, but with the coin index -1, just previous coin. And we're also adding the number that do use this coin. So if we were to subtract this value from the current amount and then use the same coin index, that would give us the value that we're looking for. But we need to handle sort of the base case over here, right? So first thing I want to say, because this over here, like we did a check for that before, right? The big enough thing. The way I'm going to handle that here is I just want to say, well, okay, if the amount ends up being less than 0, if you get something less than 0, then we'll just return 0. Makes sense, right? Same sort of thing as this, right? It's saying if it's big enough, return this, otherwise return 0. Same thing as this, right? If the amount ends up being less than 0, so if amount minus value is less than 0, in other words, if the amount is less than the value, then we're just going to return the 0 on that. Keep in mind, I mean, there's still going to be this other part. Doesn't mean the whole thing is going to be 0, but at least part of it. The other thing we need to check is if we've made it down to a coin index of 0, in that case, we want to return 1, right? Because this is the total. This is like if we're including pennies. We also want to say like if the amount ends up being equal to 0, in that case, we also want to return 1. So we'll just throw that little or in there. And now, since we've renamed this one down here, it's going to look for this making sense function up here. So let's just run this. We'll see what happens. We get the 4 for this one, but these ones are all okay. The reason this one is wrong is because, again, we're considering just all the combinations, including the ones that don't involve any pennies. So because of that, we're going to want to get our other function in here. So our other function is going to be really, really similar. In fact, I'm just going to copy paste this one for now, and then we'll sort of touch it up from there. So we do want it to be called change partial. Let's put that in, and let's not forget to change these because that could otherwise really alter the value that we're getting. Another thing we need to keep in mind is in this case, we want to say, well, yeah, if the amount is 0, return 1. But if the coin index is 0, we actually want to return 0. So quick way of handling that would just be to put that part up there, and now we can just delete that. And that should work, I think. Let's find out. So we'll run that, and yeah, okay, great. Looks like it's working. So this is like our recursive attempt over here. So we've got a recursive one, we've got our dynamic one. Okay, now the first thing I want to do with this is first I'm going to cut these, I'm going to reset the code. And again, like I said, the function that it's going to be calling is going to be this one over here. So now from here, I could just call each of these guys, right? I could do something like const result. Result 1 is going to be, making sense, recursive, the value of change. And we can say result 2 is going to be, making sense, dynamic with an input of change. Okay. And then we'll just do a quick little console log to say, okay, is result 1 equal to result 2? Okay. And then I guess we'll just say return result 1. In general, when I'm trying to come up with solutions for these things, when I'm trying to find like the right answers for the test, I usually like to follow the brute force algorithm. In general, I just kind of feel like brute force has less of a chance of being wrong, like in case we made any false assumptions or anything like that. So usually I like to trust its values, but part of the reason we're doing this now is we want to tell, are they the same? So we should expect our console to tell us true, true, true. Yeah, good stuff. They seem to be all the same. This one is true as well. Like I was saying before, the idea here is that for anyone who wants to make a challenge and they're thinking like, oh, I don't know, I don't really have like an IDE or whatever, we can do all of this right in here. It might not be the most elegant way to do it, but it's a way that you can do it. So you don't need any other special tools. We can do it. If you can use, like if you have access to codefights.com, you have everything you need to make a beautiful challenge. Okay, so one thing I'm going to do with these is I'm going to see if they're always the same. Okay, so in order to test that, I'm going to do something like this. Instead of just a console log, result 1 is result 2, I'm going to say if result 1 is not equal to result 2, then we're going to throw an error. Okay, bad error. Okay, so we'll just throw that in case they end up not being the same. So we could do something like this, and they are the same now. But if we were to just, I don't know, alter one of these guys and say something like return 2. Okay, when we run this, what we're going to find is that there's an execution error on test 2. Okay, so test 2 had an error because one of them, well, what we should have had was 4, but this one's returning 2. First one didn't have an error because we should have had 2. So it's the error because we're throwing the error over here. All right. So I just want to demonstrate that. And part of the reason I wanted to do that is because, check it out, we could do a loop. So we could say like for let I be assigned the value of 0, I is less than 100. We're going to go through 100 values over here. And we're just going to say, we'll do a few things. So we'll say, well, first of all, we're going to change the value of change. So change is going to be a random value. Math.floor of math.random times, let's say 1,000. Okay, so that's going to be change. We'll do all this stuff as well. Actually, yeah, let's just grab all of this over here and we'll paste it in. We'll need to re-indent that. And instead of returning result 1, I'm going to do a console.log of change and result 1. Okay, so basically what we're doing here is we're going through 100 different values, we're creating random values for change, we're running our two algorithms, we're comparing the results, we're throwing an error if they're not the same, and then we're console logging the input, because remember, we randomly generated it, and the result that we get specifically from the more brute forcier algorithm. So let's run that, we'll see what happens. Hopefully we don't get an error here. Okay, so notice we didn't get an error. What we got is a whole bunch of values. So this is really nice. This is super reassuring to me. This is telling me that it's very, very, very likely that this is correct, that we're actually like generating good values over here. That, well, I mean, both of these two algorithms are giving us the same value. So that's probably good. Like, I think that probably indicates that they're probably right. Okay, so that's a good little experiment. That's telling me that I have quite a bit of confidence in our dynamic algorithm. So we can probably use either of these algorithms to actually generate some good tests, good results, and stuff like that. Okay, so I'm going to alter this a little bit now. I'm going to get rid of this loop over here. And now what I'm going to do is I'm going to try to test the limits of these things. Okay, so instead of just getting the results, we're going to do a console time. So we'll say recursive. Okay, console.time recursive. This is going to use the sort of internal timer function to give us an idea of how long this is taking to execute. Now, I don't know how like consistent these things are. I know pretty much every time we run this, it's going to give us at least a slightly different value. And I've also noticed it tends to vary quite a bit depending on like where we do this. So, I mean, keep that in mind. These aren't exact or anything like that. But anyway, it's going to give us an idea. It's going to give us an idea of like how long this is going to take. So let's try running this. And okay, notice with an input of 1,000, it makes quite a big difference. It looks like our recursive algorithm is about 20 times slower than our dynamic algorithm. So that's significant. That makes a big difference. What if we made it 5,000 on the input? What would happen there? Because, I mean, we have 4 seconds to do this, right? We've had 28 milliseconds. Whoa, hey, execution time limit exceeded. Okay, so looks like for an input of 5,000, that's already too much for our recursive algorithm. I guess that makes sense because when we get to 2,000, this is already at 524 milliseconds. That's a lot. You know, if we were to make this, I don't know, 2,500 or something like that, that might be getting close to our limit here. Let's find out. Yeah, so notice that's taking over a second to do recursively. And so by the time we get to the third test, we've already spent over 4,000 milliseconds. It's not enough. So that's timing out. Now this is beautiful. This is exactly the reason we wanted to come up with a subpar algorithm in addition to our kind of ideal algorithm over here, because it shows us what's going to time us out, right? It's going to give us an idea of like what kinds of tests we can use in order to make this work, right? In order to sort of force us into something like a dynamic algorithm, something kind of smart, right? And speaking of which, like, look at how little time our dynamic algorithm takes. Like, that's incredible. This one is almost 2 seconds. This one is not even 4 milliseconds. That's unbelievable. Okay, so now we might want to say, all right, well, we have an idea of how long the recursive algorithm is taking. For now, let's just let's try to test the limits of our dynamic algorithm. So we found that 5,000 didn't work for the recursive one. Will it work for the dynamic one? Yeah, it works pretty well. It's giving us a huge value though, so that's giving us a hint that maybe we'll want to cap this. We'll want to say, actually do a mod of 1,000,000,007 or something like that, right? Because it's a huge value. And probably we'll get huger values than this because it looks like it can handle bigger numbers. Okay, we're at 18 milliseconds. That's definitely reasonable. Let's see what happens if we make it 100,000. Okay, 100,000, that's taking us 139 milliseconds. I probably don't want to go too much further than that. And you might be thinking, why not? You've got 4 seconds. You've got plenty of time. You could go way beyond that. I mean, could it handle 1,000,000, for example? And as it turns out, yeah, it sort of can, but after a few of these, it's getting there, you know? So, like, we could make it 1,000,000, and then this thing would, like, I don't know, it'd take like a second to execute. I probably don't need to make the inputs that big. I feel like, you know, we're already forcing we're forcing dynamic by having an input as big as 2,500, right? Or not much bigger than that anyway, like 5,000 was enough. So 1,000,000 is probably, I don't know. The reason I feel like, even though this, like, yeah, there's plenty of room. If there's just one test like this, then yeah, it's not going to get anywhere near the 4 seconds. But at least that's for JavaScript, right? We don't know about like Python or some of the other languages. They might take a much longer time. So we don't want to make it too like close to the borderline sort of thing. Maybe if we made it like 500,000, maybe that's better. I don't know. I feel like 100,000 is enough. I don't really see a need for us to make the test any bigger than this. I mean, that's already a pretty darn big number right there. Anyway, okay, so let's see. What did we get for 5,000? Was that enough to overflow? Yeah, that looks like that would be. Oh yeah, that's a lot bigger than a billion and seven, right? Or yeah, it's a bit bigger than it. But that didn't run for our recursive algorithm. What I'm thinking about right now, just to sort of open it up to you guys, is I'm wondering, is there a way that we can put the mod on this thing and test it across both algorithms? I don't really think there is, so I think what I'll do is I'll just put the mod on this one and we'll see what happens. Oh, I guess one thing we could do is we can make the mod like much smaller and use that to test. Yeah, maybe that's a good idea. So, okay, here's what we'll do. We'll take all this stuff and we're just going to say mod limit, and then same thing for this one. I think that should work. I guess we'll find out. So what are we doing right now? Not a whole lot. Okay, so let's return result 2. Result 2 is the one we're really interested in. So, well, first of all, let's scratch this part so that when we run this, it's just going to run. Yeah, okay, so it's still passing. It's not interfering with what we have so far. If we run this one now, what are we going to get? A value that is less than 1,000,000,007. Okay, so it looks like that's probably working. Yeah. Oh, yeah, and it's right there. Okay, anyway. Right, so what we wanted to do now is we do want to have our result 1 making sense recursive with change, and instead of these we'll just say result 1 and result 2. We'll display the two of those guys, and we'll say const limit, whoops, coinst. Oh, that's kind of funny. Freudian slip maybe? Coins on the mind. Anyway, the limit is 1e9 plus 7, and in fact we're gonna sort of shorten this to 1e6, so 1,000,007 instead of 1,000,007. And now we basically just want this part to have the limit on it, right? That's sort of the idea. Well, this part and the other part below, so the corresponding line down here. Mod limit. Okay, and now let's run that. We'll see what happens. Oh, that's gonna be too big though, right? Yeah, that's going to be too big. Okay, execution time limit exceeded on test 1. No surprise there. We'll see what happens when our input is 2,000. Okay, so yeah, we seem to be getting the same value for both of these, so that is good. Yeah, because I'm pretty sure if we didn't have the mod on there, it would be a lot larger, right? It wouldn't be like 803,320. I could be wrong about that, but yeah, it would be bigger. Okay, cool. So it looks like the mod stuff is working, unless I've made some kind of terrible mistake, which, hey, is super possible. I mean, in fact, it's likely. Anyway, okay, so that's, I think that's looking good. We've got our limit on here. We've got a working dynamic algorithm. We've got a working recursive algorithm. Now, the fun part. We can make some tests. So I guess the first thing I want to do before we go any further is just kind of verify the result for this 26 test over here. So let's make kind of a list for the possibilities, because you know that's probably a good idea before we move on. So if we've got 26, we need to make 26 coins. We need to use at least 1 penny to do it. So how could we do this? We could have 26 ones. That's one way to do it. We could have, okay, we could have 21 ones plus a 5, right? A nickel. We could have, what would this be? 16 ones plus a dime. Or it could be 16 ones plus 2 nickels, right? 2 times 5. What else could it be? I think that's the only way we could have 16 ones, right? Or the only two ways, I should say. We could have 11 ones plus a nickel plus a dime, right? 15 cents plus 11 cents. Yeah, I think that's 26. We could have 11 ones plus a nickel. No, 3 nickels. Yeah, 3 times 5. Yeah, a little scrunched. Sorry about that. And that barely looks like an 11. That's worse. Anyway, are there any other ways we could do that? So 11, a nickel, and a dime, 3 nickels. I think that's it. So we'll move on from there. We'll say if we have 6 ones, what else could we have? We could have nickel. Wait. We could have 2 dimes, right? Yeah, 2 dimes. Or we could have, I'm going to be efficient here and save some space. We could have a dime and 2 nickels, or we could have 4 nickels. Right? Yeah, I think. So what are we up to so far? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so according to this, there should be 4 more combinations. So let's find those. We could have a penny, just a single one. And then from there, we could add on a quarter to that, or we could add on, what else? 2 dimes and a nickel, so 2 tens and a 5. Or we could add on 1 dime and 3 nickels. Or we could add on no dimes and just 5 nickels. So that is 13 combinations in total. I realize that was a little tedious, sorry about that, but it is a good idea to sort of verify these things by hand. There's not really going to be anything more reliable than that when we're trying to check if the algorithm is working. So in other words, if we don't have confidence in our algorithm yet, I really recommend something like we just did, so checking it by hand. Okay. So we're almost done. We just need to make some tests now. We have an idea of what our maximum is going to be. We have an idea of we have an idea of how confident we are in our algorithm. I'm fairly confident in this, so I think we can use either of these to generate this. I mean, we ran a few tests here. One of them is we generated 100 values and made sure, well, actually, since we had 4 tests, it was more like 400 values. And they're all randomized, and we made sure that both of these algorithms are producing the same result for those. I think we have reason to be confident in these. I think it's time to make some tests. So we want to generate some tests. Here, let's make a comment. Generate tests where change is less than or equal to, what was the amount we said? Was it 100,000? I think so. Yeah, less than or equal to 100,000. Okay, cool. Well, one of the tests that we should do, for sure, is 100,000. Is that the right number of zeros? Hopefully. And we'll just say return, making sense, recursive? No, dynamic, with change. So let's try that. And we get a big number. Yeah, pretty big one. So I'm actually going to go off screen here because I'm just going to sort of keep a log of these inputs and outputs, okay? So we've got 100,000 and the output should be this pretty huge number over here. Yeah, that looks about right. Like we should expect our numbers to probably have, something like 9 digits just because of the mod that we put on it. Normally that would be a much bigger number if we were not doing the mod stuff, so, what else? What's another good change value? Any suggestions? If anyone in the chat has any suggestions for other good values, hey, I'm open to it. Why don't we go with 2,500 here, because we know that that's a value that did work for our for either of our algorithms. So that might be kind of a nice thing. It's always nice when you're making a challenge to make something that sort of where you can pass like all the visible tests using a pretty naive algorithm, but then to pass the hidden ones, you need something smarter. You need to go digging through the comments, see what people are saying about it, etc. We'll just come up with like a few other random values over here and just see what kinds of outputs we get from that. And then we're eventually going to take all these values. This is part of the reason I'm writing them off screen. We'll take these values and we'll just put them into the tests in just a minute. We'll just do some random values for now. 100,000. Okay, cool. And then I guess I probably want to do a console log so we can see what the actual input was, because otherwise we're basically just returning the result and we might think, what are you talking about? So, okay, that's a really small number. For like a random number between 0 and 100,000, for it to be 148, wow. That one's a little bigger, cool. We'll probably just use a bunch of random values over here. Unless anyone has any suggestions for better values that we can use, I think these should be fine. That's the thing. Depending on what your challenge looks like, it might be more or less complicated to do this part. Like generating tests is something that can definitely be pretty time consuming. It can definitely be something that is, not easy depending on what your inputs look like. Like if our inputs were some sort of like big matrix of strings or something like that. I mean, you guys might have noticed there was a while back where I did a series of text editor based challenges, and those were pretty tough. Like just coming up with the tests was just very laborious. It took a long time to do. So I don't know if I recommend it, but anyway. Should we put in 0? I'm a little conflicted about that. I don't know if we should put 0 in as a value, or if we should just say like, no, the values start at 1. Because like that, I guess we could say that that's maybe a potential gray area, right? 0, because like we could say, all right, well, there are no ways you can come up with a combination of coins that a given amount of 0, or there's only one way. It's a unique thing. Like, yeah, it's kind of tough. I don't know. Let's get some smaller values in here. Maybe not that small, but yeah, 100. Cool. So 78, 121 looks good. I just want like some small ones just sort of for the beginning. Ideally ones where we could sort of count them ourselves, like if you really wanted to, like we did with like the 26 and 13 one. I feel like it's actually a really good example. So we should probably add that one. Yeah. Oh, that's one we already have. Yeah, so 26 and 13 I'm going to add to my list over here. And I don't know if we should add any others for now. This is probably quite a few. I don't know how many I have here, but we'll find out. Anyway, now that we want to add tests, keep in mind, we don't want to just go to add custom test for this. We want to go specifically into this part here, edit the challenge, and now go to add test. That's really important. Okay, so first thing we want is our 26 and 13. We found that was a really good test, so we'll include that one. Next one is our 78 and 121, at least in the order I have them listed over here. 66 and 87. What else? Probably don't want to get too much into the super big ones quite yet. Although I should probably mention we can change the order of these things. So, don't worry too much about like how you put them in. I'm just kind of thinking because we can basically like, we can drag these things around like with like the up and down arrows. It's not a super easy thing to do. Like ideally we want to probably minimize the number of clicks we have to do for this. So, something to keep in mind, I guess, but we can definitely reorder them. That's not like a problem or anything. What's next? It's generally a good idea to have a lot of tests, a good diversity of them as well. We want to try to be sure that we're including like all the edge cases. We don't want to allow an algorithm to pass that's kind of like suboptimal just because we didn't happen to test for all the right conditions. So that's probably worth keeping in mind. I'm noticing not a whole lot of these values that we're using as inputs are multiples of 5. So we probably want to put in more of them that are multiples of 5. The reason I say that is because if it's not a multiple of 5, we can just get away with using like just a single dynamic programming array, or just a single recursive function, because we found that we wouldn't need the other one if we were looking at just the combinations, or if we were looking at a number that only had combinations of coins that involve pennies. So pretty much anything that's not a multiple of 5, that'll be the case. So we've got how many tests now? 16? That's pretty good. I should probably take this opportunity to mention that, and this is kind of important in terms of how we order our tests, anything that is less than or equal to the number of tests divided by 2 is going to be visible. Okay, so basically the first half is going to be visible, and it's generous about that. So if we were to add one more test so that it's 17 instead of 16, we'll do the 0 and 1 test, because we might as well. We'll just move it up a bit anyway. So now that we have 17 of these, there should be 9 visible, 8 hidden. Okay, so the first 9 the user is going to see. So be mindful of that, like don't reveal too much if you don't want to, sort of thing. Anyway, let's save this, and we'll get rid of this for now. Console log change, making sense, dynamic change. Okay, so it is failing just one of these tests, and it's this one over here. For a change of 0, we're getting an output of 0. Expected value is 1. You know what? I'm going to drop it. I don't think we should keep this one. I don't think it's worth keeping this one. So instead, let's just get some others that are like multiples of 5. So let's say 20. Actually, maybe 50 would be good for for a smaller one, because yeah, we could do 2 quarters. Yeah, I think that would be nice. So okay, what's our answer here? Console log change. I didn't mean to make it a randomized value. I meant for it to just be 50. Okay, sorry about that. So 50 and 39. I'll just make a note of that, and then maybe let's get like a pretty huge one. I guess we did 2,500 already, right? Maybe 5,000 or 5,075, just to make it a little more interesting. Okay, cool. So for 5,075, we get a very interesting number. Very cool. All right, so that's good. We're let's see. That's 2 additional tests. So what would that bring us up to? We're going to delete 1, right? So that'll bring us up to 18. So I think we're good. So let's add these now. So what was it? 50 and 39 was one of them. That's good. And the other one was 50, 75. And the answer is this big thing over here. So, okay, cool. Put that in. And I just want to make sure the tests are in a good order. I want this one to be visible. I want everyone to be able to see this. So we'll just move it way up there. That one should be the last test. This is just a personal preference thing, but I generally like to keep the toughest test as the last one. The reason is because if this is a test where you're probably going to be timing out, I want to make sure that the user is going to pass as many other tests as possible before getting to the one that's going to make them time out. So, yeah, that's basically the reasoning there. So we're more or less going to try to make these go up, like, for the numbers to increase as the test number increases. Yeah, we're going to can that one. Oof, that's pretty big. Oh, that's really big. Jeez. Yeah, so that should go to 17, I think. Where are we now? Yeah, okay. Cool. All right, so I think that's good. 18. So this will be, yeah, okay, cool. So all of these will be visible. All right, nice stuff. I guess we'll need to sort of decide on like which tests we want to use for the example. And I guess speaking of which, if we're all done now with our tests and if we're happy with this, then I guess we can probably move on to the next step here. So let's do that. All right, so for making our description, writing a nice description in particular, there are a few things to keep in mind. There are a few standards we want to make sure that it lives up to, sort of thing. So first things first, we're going to hit the crayon icon again to get into the edit mode where we can edit the description and all those wonderful things. So let's do that. This isn't all that descriptive, so we probably want like something a little more fun in terms of our description over here. But before we even get into that, I'm just going to expand these a little bit because I want to talk about these fields. These are some of the more important fields because most users are going to look to these to get an idea of what the guaranteed constraints are going to be. We can use Markdown here, so that's what these little asterisks are. That's going to make this text italic. We can also make it bold by doing double asterisk or underscore. We'll look at that in just a minute, but the standard for this is that it's italicized. Guaranteed constraints. Okay, now in terms of what our constraints are, there's not that much to say here. We can also sort of use HTML in here. So I'm going to say code, and we'll say 1, right? Because we want it to be at least 1. And we'll say less than or equal to change, which is less than or equal to 100,000, which we're going to represent as 10 with a superscript of 5. Okay, so it's got to be at least 1, at most 10 to the power 5. That's what we're saying there. And what is it? It is an integer representing the amount of change you're owed in cents. I guess we should have specified that a really long time ago, but anyway. In terms of our constraints, by the way, before we move on, I just want to say sometimes, like if our input is an array or a matrix or something like that, sometimes we'll find like multiple lines here because we'd say, okay, the length is between this and this, the elements are between this and this, etc., sort of thing. You know, we might even say like the length of each row is always going to be equal to the length of previous row plus 1, or like something like that. You know, anything that's guaranteed we probably want to include in there. What are we expecting as an output? We're expecting an integer representing the number of possible coin combinations with at least 1 penny. Yeah. Okay. Yeah. I think that's probably good enough. We could change it if we really wanted to. Change. Anyway, the point is, we've got these. This is probably good enough, but we'll see. I mean, look, here's the thing, right? We submit this challenge. We might find that maybe the admins are going to make some edits to our description, make it more clear. Maybe even after that, once the challenge goes live, we'll find that there's some comments, people asking questions like, "Oh, is it? Are you sure these are guaranteed? I found one that's bigger or smaller, or something like that, right?" And then we would adjust as need be. So keep that in mind. You know, we'll get useful feedback at a few different stages for this. Okay, so let's jazz up the description here. Let's make it something kind of fun. This is a question about Canadian monetary system, right? So I'm going to try to immerse it in kind of Canadiana a little bit here. So you and a friend are on your way to go hiking in the Gatineaus. And you've decided to stop in the Byward Market for some breakfast. You order a large double-double, 2 beaver tails, a small poutine, and a box of Timbits. Breakfast champions. You pay for the food, and as you're waiting to receive your change, you start thinking about how many different combinations of coins could be used. In Canada, I should probably capitalize that, there are 5 types of coins. Now we can do a bulleted list here. There's a markdown thing, so one way to do it is to use an asterisk. I think you can also use a hyphen, but anyway, then make sure you put a space in. I'm pretty sure that's important. We have a 5-cent coin called a nickel. We have a 10-cent coin called a dime. We've got a 25-cent coin called a quarter. A 100-cent coin. Kind of weird to say 100-cent coin instead of a $1 coin, but just to be totally clear, for the purpose of this problem, we don't really need to think about conversion from like cents to dollars and vice versa. Anyway, a toonie. Okay, cool. So there also used to be a 1-cent coin known as the penny, but it was removed from circulation in 2013. You're wondering how many more combinations would have been possible if we still had pennies. Given an integer change, I'm using backticks around the word change so that it appears as monospace code, representing the amount of change you're owed in cents. Find how many combinations of coins could be used that would include at least 1 penny. Okay, so that's a little more descriptive. It's a little more fun than what we had before, which is nice. We're not quite done yet, though. We need to include 2 other things. So the first one is an example, and the other one is actually just a little headline here, a little header for input/output, because that's what the stuff underneath over here is going to be. It's going to be the input-output stuff, so we're just going to manually put in that little title there. For example, usually it's pretty typical to just use the first test as the example, so I guess we might as well do that. So we could say for change is equal to 10, the output should be making sense of change is equal to 2. Okay, and now since I'm in like a bulleted list, an unordered list over here, I want to make sure that the indent is going to maintain on the next line over here. So I'm going to say, I'm going to just put 2 spaces, and Markdown is going to detect that as being the same indentation. So what do I want to say here? There are 4 possible coin combinations. So also doing the indent, so I'm going to get another another level of indentation for this. So we're going to have like a second level of different styled bullets, which will be nice and exciting and fun. So 4 possible coin combinations. What are they? We could use 10 pennies, or we might as well use, 10 pennies. What else? We could use 1 nickel and 5 pennies. We could use 2 nickels, or we could use a dime. And then we'd say out of these combinations, only 2 of them include pennies. So the answer is 2. Okay, cool. And then we'll put another example here. More examples the better, I would say, within reason. It's pretty close to the last one, but, that's okay. Sometimes that's actually the best thing we can do. Making sense, a change should be 4, right? I think it was. There are 4 possible coin combinations. What are they? We could say 11 pennies, 6 pennies, didn't mean to double up on that one, 6 pennies and 1 nickel. We could say 1 penny and 2 nickels, or 1 penny and 1 dime. Okay. Then we can say all 4, I think I spelled out the word above, right? All 4 of these combinations include pennies. So the answer is 4. Okay, cool. And that should be good, I think. Let's save it up. Let's just verify, yeah, 10 and 11. So that's nice. Yeah, it's always nice when these sort of match up with the actual tests over here. I think it looks good, nice formatting. We've got the double, like 2 levels of indentation here. I think it looks really clean. Now, we might want to also, like if this was a challenge that was like a bit harder to understand, a bit harder to visualize, then we would probably want to include some sort of picture, like a visual aid to sort of help us understand what the problem's asking. But anyway, I think this is probably fine over here. I don't think we need to worry about a lack of clarity. And, you know, if we do, we'll find it in the comments. Someone will probably eventually mention that. Now, something I just want to say before we wrap up here, because I think we have a pretty good challenge. In fact, you know what? I'm just going to delete all this stuff over here. I'm just going to say making sense, get rid of the dynamics. So it's just making sense. And we'll try running the tests one more time, make sure those are all working. Very good. Did we have any custom tests still? Yeah, we did, but we can delete that. Okay, cool. So 18 tests, we're passing them all. Let's go ahead and submit our solution. Now it's going to tell us the challenge isn't active, so your solution won't appear on the leaderboard. How'd you rate our IDE? Hey, I think it's great. Okay. Nice stuff. Feedback saved. All right, so now we can see that our solution is over here, right? So we could like click on that and it's visible to us. It won't be visible to other people, but well, actually, sorry, that's not entirely true. This will be visible to the admins when you submit it. And that's really important because it means that they'll have a very clear sense of what your intention was for this problem. They can also use your algorithm if they wanted to generate more tests or, you know, compare to see if they're getting the right result. So I highly, highly recommend including a solution to your challenge when you submit it. But keep in mind, what we have now is what I would consider more or less a perfect challenge. You know, we have a simple idea with a pretty complex solution. We have something that starts with like very simple inputs, simple outputs, but there's a lot happening in between. I love it when that happens. Another thing is that it's very descriptive. We've got a nice story attached to it, but there's a great algorithmic idea that underlies the whole thing. So I think that's really good. But keep in mind, when you submit a challenge, it doesn't have to be perfect. I don't want you thinking, oh, well, I can't think of anything perfect. I can't think of like a great story, so I guess I just won't submit anything. You know, I want you to feel like no matter what, if you've got a good idea, that could be a great challenge, okay? If you're having trouble coming up with a story, hey, we can help you with that. If you're having trouble coming up with some of the tests or even writing the algorithm, I mean, that's probably something that we can talk about. So I don't want anyone to feel discouraged if they feel like, oh, I don't know if I can handle all that. Like, the main thing is coming up with a great idea. And you know what? I know you have some great ideas. So that's going to be it for today. Thanks for tuning in. I hope you guys feel empowered to go and create your own challenges now. Again, like I said, we can keep an eye on the challenge that we made. We just go to the all statuses thing here and go to created. And we've got making sense over here, our challenge that we created. And we're just sort of waiting for the admins to approve it and post it as a daily challenge. Something I should also mention is you're very likely, upon submitting this, you're very likely to get a message from Zero Cool about your challenge. Just some questions, looking for clarifications, stuff like that, asking if it's okay to make some changes, these kinds of things. Okay, so we'll open up the lines of communication if you submit a challenge, or at least it's very likely. So, thanks for tuning in. Best of luck to you in creating your own challenges, but I think we both know that luck has very little to do with it. It has to do with the great ideas you have and the tenacity to pull through and actually submit them. So, looking forward to that. Have a great day. Remember to believe in yourself. Anything's possible. I'll see you guys later. I love you all very much. Bye.